So it's 2025 and it feels like we're seeing a bunch of ways to generate visual content with AI, mainly with these diffusion models that generate images from text. If you look online, there's a bunch of tutorials on generating free game assets with services like Midjourney. OpenAI even lists game development as one of the primary use cases for their image generation feature. I'm sure that in the near future, there's going to be widely available services where you'll be able to just type in a prompt and get a whole 3D model out. While this is very impressive from a technical angle, there are a bunch of practical issues with generating visuals like this, such as being very computationally expensive, having limited control over what the model generates, and exposing yourself to potential plagiarism issues. At the same time, it's not like the idea of generating stuff in a video game is a bad idea, because we do this all the time. I'm talking about procedural generation here. Unlike a lot of methods trained directly on images, procedural generation tends to be computationally cheaper, gives artists a lot of direct control over the final product, and there's way less of a chance that something that's generated already exists. In this video, we're going to create a program that'll assemble a Lego model based on a provided class. More generally, the technique we'll use can be applied to any procedural generation algorithm where you assemble a model piece by piece. Here's a random example of a situation where I think it'd be cool to use this. Let's say you're making a game where you're fighting robots, and when they die, they drop parts. These parts can be used to create or upgrade weapons. To streamline the experience and add a bit of novelty, instead of having the players literally construct each weapon they want, or having the players select from a fixed set of weapon models, we want the game to generate new weapons for us. We want to create this loop where players beat up robots, collect parts, throw those parts at a crafting machine, get a unique weapon out, and then go back to beating up robots. Turning an arbitrary set of parts into distinct weapons can be pretty tricky to do with more traditional procedural generation algorithms, but with ours, we can just teach a neural network to do it for us. Back to building with Lego bricks. Just to make things harder on ourselves, we'll also add the constraint that we're not allowed to train on a huge dataset of existing models. This is for two reasons. The first is that in practice, you aren't going to have an existing dataset of models generated by your procedural generation algorithm. The second is that if I just downloaded a bunch of Lego models and trained on that, people will get upset, as they should. Before we start, it's worth seeing how good off-the-shelf solutions are at this sort of thing. I did just complain about text-to-image generators a couple seconds ago. So let's try to generate a Lego model of something that there isn't a million images of. We'll go with a hairdryer. This looks good at first glance, but if you look closer, it's pretty obvious that these models are impossible to build. This one looks kind of okay, but most of these aren't even made of Legos. Still no.
He mentioned something interesting. Cypher is pursuing new research. He claims that what they're doing in Africa is the missing piece. A weapon to surpass Metal Gear.
I think we've seen enough. Let's describe some of the prior art first. The book Procedural Content Generation via Machine Learning, an overview, describes different ways of combining machine learning with procedural generation. We'll be using what the book calls a constructive approach, where on each step, we'll perform one step of our procedural generation algorithm. Each step consists of selecting the next thing our algorithm should do. Rather than hand-coding a set of rules dictating which choice to select on each step, we'll instead learn an algorithm that'll do it for us. Our approach is inspired partially by approaches that use classifiers to generate content. Most famously, clip-guided diffusion uses a clip model to guide a pre-trained, unconditional diffusion model towards certain types of content. Another inspiration is Lego Combinatorial optimization algorithms. There's a lot of work in this field, but the most similar work I found was brick-by-brick combinatorial construction with deep reinforcement learning, which uses reinforcement learning to generate Lego models that match a certain volume. Unlike them though, what we're trying to do is generate models that match some concept, instead of mirroring a physical quantity like volume. BrickGPT, which came out recently, is another project that generates Lego models from a written description. Their approach takes a dataset of 3 models, voxelizes them, converts the voxels into a Lego model, then trains a language model to output the parts of the model given a textual description. This does mean that you need a dataset of 3 models beforehand, and the models you end up with have to map to a voxel-like representation, which doesn't always work. Like we just mentioned, we're going to treat this as a reinforcement learning problem. To do this, we need to figure out how to structure a problem, then choose a learning algorithm. Quick side note, we're going to be working with both Lego models and neural networks, aka machine learning models here, so to prevent confusion, I'm going to refer to Lego models as models, and the machine learning model as a neural network. Our procedural generation algorithm is pretty simple. Starting with a single 2x2 block, we add a single piece to the model over and over again until we've done this 16 times. We'll use 8 types of basic Lego pieces, shown here on the screen. It might not sound like there's a whole lot of unique models you can build under these constraints, but we've got 16 steps, and on each step, we choose one of 8 blocks. We end up with 8 to the 16, or over 200 trillion different possibilities like this. And that's not even counting the number of different ways you can place a block. In fact, there's so many ways of placing a block that we need to limit the number of blocks the algorithm can select from. We're just going to choose up to 100 random candidates, which is definitely not a whole lot, all things considered. Reinforcement learning problems are designed to solve Markov decision processes, or MDPs. MDPs break a problem into a series of steps, where on each step you get the current state, perform an action, and get a reward. Based on the procedural algorithm we just described, our state in this case is the current state of the model, and our actions are the part we add to the model. Now, all we need is some kind of reward. How do we tell our algorithm to do something like generate stuff that looks like a dog? 20 years ago, this would have been a really difficult thing to do, but in 2025, this is actually pretty easy. We're going to be using an off-the-shelf image classifier called Clip. Clip has been trained on thousands of image text pairs, so given a set of labels in an image, we can determine the most fitting label for that image. It does this by encoding each label in the image into a vector, computing the cosine similarity of each label to the image to get logits, then normalizing these logits through softmax to get probabilities. We'll set up an ad hoc vehicle classifier by using the labels shown here. We can now render a completed model and run it through our classifier to get the likelihood that this image belongs to a certain class. To make the algorithm's job easier, we'll mirror the model on its x-axis before rendering, so it doesn't have to worry about symmetry and we end up with more complex models. The hope is that by using class probability as a score, the algorithm will be incentivized to generate things that look like that class. In a quick test using models I searched for on Google Images, Clip almost always classifies LEGO models correctly, so we have that going for us. We'll be using the Deep Q network algorithm, otherwise known as the DQN, to train the network. The basic idea behind this is that we're going to train a network to predict what the return, or sum of rewards, for each action in a given state is, assuming we always choose the best action from here on out. Our LEGO construction problem is set up so that on each step, we have the current model plus a list of potential parts and their placements. If we expand this out, we get a tree of possible models and how they're constructed. We want to figure out how to consistently get to the best models in this tree through our actions. To do this, we'll initially perform random walks. In each walk, otherwise known as a trajectory or episode, we'll keep track of the state we visit, action we take, and the state we end up at. We'll also keep track of the reward we get for performing an action and whether or not we finished, although in this case, we only get rewarded at the end, when we score the model. Each of these state, action, reward, done, next state tuples is called a transition. During training, we sample a bunch of transitions and train the model to predict the return we'd get if we choose the transition's actions and then always perform the most optimal action. This is a reward plus the predicted optimal return of the next state, which we calculate by taking the maximum predicted return of the next state. If this is the last step, we only use a reward, not the predicted return, since there's no more actions you can take. As you train, the steps towards the end learn to accurately predict the value of final states, then the steps leading to those steps, then the steps leading to those steps, and so on. As we get a better and better prediction of these returns, we slowly lower the randomness by sometimes using the best action according to our network, which helps us explore better parts of the search space. The hope is that once we finish training, we can figure out which placements lead to good models by just checking the expected return of candidate actions, according to our network. We've talked about our problem and the algorithm that'll solve it, but there's still one more thing we need to bring up, the network itself. What most people think of when they hear the term neural network is a stack of linear layers with activation functions between them. This network takes in a fixed set of numbers as input and outputs another fixed set of numbers. This is great if you're trying to predict housing prices from geographic features, but our state is made up of a set of blocks that we can add and remove from. Let's start by giving the data some structure. A model is made up of a series of discrete connected parts, with each piece having its own position and orientation. We can describe a model as a graph of placed pieces, where pieces that are connected in the model are connected in the graph. Edges don't contain a whole lot of information, only that two pieces are connected to each other. Nodes, on the other hand, contain quite a lot of information. The piece being used, its orientation and position, its bounding box, and which of its connectors are used up. We also add the class of the model we want to generate and the step count, which are technically global properties of the model and not node-level features, but it's easiest to just add this information to each node. We'll encode each piece of information into a node vector that represents the value of this node as a series of numbers. Now that we've converted our models into a graph, we're actually going to process them with graph neural networks, more specifically, graph convolutional neural networks, or GCNs. For each node in a GCN layer, we average the representation of all neighbor nodes, add them to our node's current representation, then run this new representation through a linear layer and activation function. Our new representation takes into account neighboring features, allowing information to be shared across connected nodes. There's a really nice interactive resource on graph neural networks that I'll put in the description if you want to read more about them. We'll stack several of these layers on top of each other to get a good amount of expressiveness. We'll also add a layer at the beginning that just linearly maps each node to our hidden dimension, and a layer at the end that linearly maps each node's features to a single value. This has been described as the encode process decode architecture. To allow the network to select parts to add to the model, we'll add candidate placements to our models as nodes with edges directed from the part they're connected to the candidate part. This means that inside a GCN layer, the representation of an action node will be updated by the representation of the part it's connected to, but not vice versa. So, no matter which candidates we add to the graph, it won't affect the representation of the model itself. We'll start out easy with 3 classes: skateboard, rowboat, and spaceship. Oh no, these models are bad. But even worse, our network is failing to figure out how to optimize this problem. This graph shows the reward our network was able to get over the course of training. As you can see, it peaks close to the start, but it's downhill from there. We'll try to fix the second problem and hope that fixes the first. A look at the value estimation curve shows us a problem. We're overestimating the return from placing a single block. This graph shows us how much reward the network thinks it's going to get during each episode as training progresses. Since our rewards are in the range of 0 to 1, and each episode takes 16 steps, the maximum value on this graph is 16, where on each step, the network predicted a reward of 1. Clearly it was getting way less reward than this, so the network was really wrong towards the end. Overestimation is a problem with DQNs, since you're replicating backwards the largest action value. In our problem, if the predicted value of choosing any block gets super high, the value of the previous action increases, then the action before that, then the action before that, and so on. Neural networks are approximators, so unfortunately, we can expect the network to make all sorts of errors during training. This also makes it difficult to scale the problem in network, since doing both only makes the problem worse. I tried a bunch of small changes, but nothing really worked. I was starting to wonder, if overestimation is getting this bad, is the network correctly predicting even the final step's reward? Because if it can't, then there's no way the other steps are going to train correctly either. To combat this, I initially increased the probability of sampling the last step during training to 25%. In other words, a quarter of the items in each batch should be just the last step. This caused the expected return to flatten as soon as it reached a reasonable level, which is exactly what we want. And here's where I got stuck again. No matter what I did, I couldn't get the performance to increase much past this point. I tried a bunch of things, trying a variant of end-step returns, using polyac updates for updating the target, setting exploration to a low value. I even tried manually constructing a couple models and pre-training on that data. All of these things either only gave a slight improvement or ended up actually hurting performance. With nowhere else to look, I decided to take another look at the network itself. After looking a bit more into graph networks, I found that just stacking a lot of GNN layers together tends to actually give you worse performance. The original GCN paper found that using skip connections helps, where for each graph convolutional layer, you add the input of that layer to the output, allowing every layer to directly contribute to the final output. This has traditionally been used in deep image recognition architectures to help stabilize learning. So let's see if that helped at all. Huh. So let's take a look at these models and see if we can call it a day. Okay, so what happened here? Well, remember that when we used clip as our reward, we took a set of text labels and compared against each of them, normalizing the logits with softmax to get a probability distribution over each label. We then took the target's class probability as our reward. This is how clip was trained, and it's how you're supposed to use clip for image classification. The problem is, this can incentivize the network to produce models that don't necessarily look like the target class, but look even less like other classes. For example, take a look at the skateboards we generated. These long shapes don't look anything like skateboards, but they look even less like rowboats and spaceships. So our classifier assigned high scores for each of these models. I fixed this by switching over to raw dot product similarity between the label and image vector as the reward function. That looks a bit better. At this point, I was wondering whether I just chose a really bad set of classes. While I was putting together models manually, I realized that I was having a hard time generating models of these categories. So I decided to switch to a new set of classes. We're generating furniture now. Here are the classes. I also found that generating multiple classes at once was giving me a lot of trouble, so we're only going to be generating one class at a time. With everything put together, we're finally able to generate good looking models. In this case, chairs. Let's take a closer look at them. Every model generated by the network has a backrest and a seat. The backrest tends to be reclined and often has a slight curve at the top. Other than these two essential chair features, like chairs in real life, these generated chairs vary quite a bit. Some of these models have legs, while others are kind of rooted to the ground. Some of them have armrests, while others don't. I also noticed that sometimes the network adds a footrest to the chair, which is something that you usually don't see on chairs, but there definitely are chairs that have that feature, like barber chairs and some office chairs. The other models didn't turn out super great, but you can kind of see what the network was going for. For beds, couches, and tables, the network converged on these long horizontal shapes. I did notice that the beds tend to be flat, while the tables have these stubs at the bottom that look a bit like legs. Couches have this sort of W shape, possibly to make them look like armrests. The lamps are pretty interesting. The network consistently generates this specific shape, basically a cylinder with wheels at the top. I think it's trying to go for a table lamp, where the wheels are supposed to be bulbs, and the part at the bottom widens to look like the body. Finally, stools. It looks like the network learned to generate both chair-like shapes and more bar stool-like shapes, since both are technically stools. I might be reading a bit too much into it though. Let's recap. In this video, our goal was to create an algorithm where you can supply categories to generate, and it would learn to generate those items. While the models we ended up with aren't going to win any awards, and we had to train with each class individually, we can generate pieces of Lego furniture now, just by passing in the thing we want to generate. I tried a bunch of different things to get this to work, but I'd say the biggest differentiator was increasing the probability of sampling the last step. Doing that not only prevents the model from incorrectly guessing how good models are, which you saw kills overestimation, but also converts the problem into a sort of supervised learning problem, which I suspect stabilizes the learning process. As I mentioned before, I think that neural procedural generation is a better path forward to integrating machine learning into the artistic process, particularly for game development. Because you specify both how something should be created, as well as a criteria to judge them, you have way more artistic control over the things you generate. Of course, we're not quite at the point where we have something game ready. Here's a couple ways I think this approach can be extended and improved in the future. In this video, we just used Clip to guide the network towards models that fit a certain class. A related but potentially more useful scoring function could take advantage of modern visual question answering models to guide conceptual aspects of the model. For example, at the beginning of this video, I brought up the concept of a game that turns robot parts into weapons. Directly using our clip-based reward probably wouldn't work super well, since our goal is to generate unique weapons with different capabilities. If we just ask Clip if a model is an axe or a gun, you probably wouldn't end up with very interesting models. But what if we asked the VQA model things like, does this weapon have a rangefinder? Or does this weapon have a blade? You can incentivize the algorithm to generate models with specific features instead of just maximizing the similarity to a single class. Here's another thing I'd like to try. Part of the reason why this problem is difficult is because you have a large space of things that can be generated, and you don't get feedback about how good a generated model is until the end. This is actually pretty similar to games like chess and Go, and I feel like you can use the same technique algorithms like Leela Chess and AlphaZero used, integrate and search. During training, instead of either performing a random action or the action the network suggests on each step, we would instead try a bunch of different actions, using our network as more of a heuristic instead of a source of truth. This would allow our algorithm to focus on higher quality models during training, potentially getting us better results at the end. Finally, I'd like to see better ways of selecting an action. In a real-world procedural generation algorithm, you need to select from potentially thousands of different options on each step. That's a lot of things our neural network needs to compute. To deal with this, we just selected a random set of 100 options and asked the network to choose the best one. This ended up working okay for our use case, but you can imagine cases where the models generated end up being suboptimal because an action it expects to be able to take isn't available. One better way could be splitting action selection into 2 steps. On the first step, you select the block you want to attach to, while on the second step, you select the part and placement of the attaching block. That's how algorithms like AlphaStar handled its large action space. I think adding these things could really help improve the algorithm. I haven't actually done these things in the video though, so I'll throw out a further research is needed here. I've got code in the description. Thanks for watching, and I'll see you in the next video.